In this problem, we're considering a pool of college applicants. Here they are. And we're partitioning this pool of applicants in a way by considering the people who are good at math, the people who are good at baseball, people who are good at both, and the people who aren't good at either of those. And the acceptance criteria for the college is if the student is good at math or baseball or both, accept them, otherwise reject them. So everyone who is good at math and everyone who is good at baseball and everyone who is good at both get accepted, whereas the people who weren't good at either get rejected. And the problem asks us to explain intuitively why it is that amongst the population of accepted students, amongst this population, information, so amongst the accepted students, information about the student being good at math is negatively associated with the student being also good at baseball. So what that means is, given that we've been accepted, knowing that we are good at math makes it less likely that we're also good at baseball compared to not knowing that we're good at math. Just knowing that we are an accepted student, and just considering the likelihood of being good at baseball. So this is what we need to explain. One more condition that the problem gives us is that being good at baseball and being good at math are independent of each other. So let's see why this may be the case. Let's consider the probability of being good at baseball given that we've been accepted. So this probability is the number of students who are good at baseball, the number of students good at baseball over the number of students good at baseball or math. Let's say or both. Notice that in the numerator here, I'm not writing the number of students good at baseball and having been accepted, although that is the definition of conditional probability. And the reason I'm not writing the number of students good at baseball and accepted is because if a student is good at baseball, they've automatically been accepted. That is one acceptance criteria of our college. If you're good at baseball or math or both, you're automatically accepted. So saying that you're good at baseball automatically means you've been accepted. Now let's consider the probability of being good at baseball given that you've been accepted to the college and you're good at math. Well, notice that saying that we've been accepted and saying that we're good at math is redundant, because if we know we're good at math, then we know we're accepted. That's also acceptance criteria of the college. Being good at math means you're accepted. So we can rewrite this as probability of being good at baseball given that we are good at math. But we were also told that B and M are independent events. And so this is just equal to the probability of B. Now what is the probability of B? The probability of B is the number of students good at baseball, is the proportion of students who are good at baseball over whole population of applicants. Now, the size of the population of applicants is larger than the size of the population who are good at baseball or math or both. So here was our whole population. Here were the people who were good at baseball, math, or both. And so since the population on the left is larger, the denominator here, this denominator is larger than the denominator here. And so we see that the probability of B given A, comma M is in fact smaller than the probability of B given A. So this is the intuition behind why this is the case, it's because in one computation, we're considering our context is the whole population of applicants, whereas in the other computation, our context is just the number of people who are good at baseball, math, or both, which is a smaller number of people. So that probability here, probability of B given A, becomes larger than the probability of B given A and M. So in part B, we're asked to sort of rewrite this, but in a more general, in a more formal setting, and the setting is the following. So we're given two sets, A and B, and we're told that A and B are independent, and we're given C, which is their union. And it's a good idea to try and relate this general setting to the example that we just discussed in part A. So A and B could be thought of as being good at math. B could be being good at baseball. And then C is the population of admitted students. So students who are so this is the accepted population. This is students who are either good at math or they're good at baseball. And we'd like to show that A and B are conditionally dependent given C. So meaning the probability of A given B comma C is less than the probability of A given C. So conditional on C, A and B are dependent. And this is exactly the question we just talked about here, that conditional on the student being accepted to the college, our two sets M and B were dependent, as we showed. So again, in this case, conditioned on the student being accepted to the college, our two sets A and B, we're trying to show that they're dependent, A and B in this case. And so, again, we can say, well, telling us that C has occurred and B has occurred is redundant, because if we know that B has occurred, we know that C has occurred because C is the union of A and B. And so we can rewrite the left side as just A given B, but we know that A and B are independent, so that's just probability of A. And by the same argument as we discussed above, the context when talking about the probability of A is the whole sample space. And it's going to be less than the probability of A given C, because when we consider when we condition on C, the context just becomes our set C, whereas the context here on the left, when we're considering the probability of A, the context is the whole sample space. The same argument as in part A.